Hello, friends. Welcome to the third lecture of Bayesian Inference. In this lecture, we will see the loss function. Before going to start loss function, we will discuss some basic definitions. So, first one is conjugate prior. For a given likelihood, if the prior distribution leads to be a posterior distribution belonging to the same family as the prior distribution, then this prior is called a conjugate prior for this likelihood. That means the likelihood function determines which family of distribution will lead to conjugate prior. That is a prior and posterior distribution that come from the same family. Okay. Conjugate distribution can be formed by selecting family of distributions that has the same algebraic form as the likelihood function, treating the unknown parameter as the random variable. Okay. Uh, Means for example, in last lecture we have seen that one example, that is if your x follows binomial with n comma p and your prior distribution, that is pi of p, which is your 1 upon beta ab p raised to a minus 1 1 minus p raised to b minus 1. That means this p follows beta first kind ab, where your p is lies between 0 to 1. Okay. So after solving, we get the posterior distribution. That means this posterior p given x follows beta first kind with parameter x plus a and n minus x plus b. Okay, so this is again the beta distribution of first kind. This is your filter, means the prior and posterior has come from the same family. So that prior is known as conjugate prior. Okay, so using conjugate distribution often makes Bayesian calculations simpler. They may also be appropriate to use where there is a family of distribution that might be expected to provide a natural model for the unknown parameter. Okay, uh, one more case, improper prior distribution. Sometimes it is useful to use an uninformative prior distribution, which assumes that an unknown parameter is equally likely to take any value. For example, we might have a sample from normal population with mean mu and sigma square is known. Okay, where we know nothing at all about mu. This leads to a problem in this example because we would need to assume a uniform minus infinity to infinity, which is just assume that your mu has uniform minus infinity to infinity, which doesn't make sense since the PDF of this distribution would be zero everywhere. We can easily get around this problem by using distribution uniform minus n and n, where n is very large number and then letting n tend to infinity, the PDF of this distribution is 1 by 2 n. Okay, and which is constant. If we use the proportional to method described above with the prior distribution proportional to 1, everything works out nicely. Even though the range of value is in this sense infinite, we have in fact used an uninformative prior already in the light bulbs example and in the pack of cards example. Okay, so that case your improper prior distribution is there. Okay, and one more definition which is necessary for the Bayesian is hyperparameter. Okay, so hyperparameter is just the parameter of prior distribution. Okay, this is your hyperparameter. Means what? The parameter of prior distribution are called hyperparameter. Okay, again parameter of prior distribution. So now we have to come to the our topic, that is loss function. Okay. To obtain an estimated theta, a loss function must first be specified. This is a measure of the loss incurred when your g of x is used as an estimator of theta, or estimator of that parameter theta. A loss function is sought which is zero when the estimator is exactly correct. That is, g of x is equal to theta, and which is positive and does not decrease as g of x gets further away from theta. There is one very common use loss function, and this loss function has uh, three types, that is quadratic or squared error loss function, absolute error loss function, and one more is all or nothing or 0 and 1 loss function. Okay, these are just the three types of loss function. Before going to start these types, we firstly discuss the what is mean by loss function. Okay, so here I have to take the definition of loss function. Let fx theta belongs to parameter space be a family of PDF and x1 x2 xn be a random sample from this distribution. Once the sample points are observed, we can take an action on the basis of this data. So let A be the set of all actions or decisions. Okay, a decision function g of x is a statistic that that takes values in a and your g of x is a Borel measurable function that maps R into A. Okay, that is, let A be an arbitrary space of actions. A is non-negative function that maps parameter space multiplied by your action set of action set and which maps to the R. It's called as loss function. Suppose this L is mapping from theta into A to R. So this is your loss function. Okay. So generally, uh, there are three types of loss functions. One is squared error loss function, or which is also known as quadratic error loss function. Okay. Second one is absolute error loss function, that is AL, and third one is all or nothing, which is also known as 01 loss function. Okay, so you can call it as all or nothing loss function or 01 loss function. Okay, so we will discuss this all three loss function in the next lecture. But remember that in the Bayesian estimation, you want to follow the five important steps to finding the Bayesian estimation. So first step is, firstly, decide appropriate prior. Then write the likelihood of random sample. After, obtain the posterior distribution. Further, decide loss function, and finally obtain the Bayes estimator by using this loss function. These are the just steps for finding the Bayesian estimation. After studying these three loss functions, that is squared error loss function, absolute error loss function, and all or nothing loss function, we will discuss the weighted squared error loss function in next lecture. So all these three loss function and using squared error loss function, we generalize it, uh, weighted version, which is weighted squared error loss function in next lecture. Okay, so thank you Thank you so much.